Welcome back to the video course on fluid mechanics. So, now we will start a new chapter, dimensional analysis. So, dimensional analysis is one of the important aspect in fluid mechanics, since fluid mechanics to do various experiments for the various analysis or investigation purpose for our theoretical development, we will be doing number of experiments especially, and in these experiments there will be, say, we have to have a large set of data to be generated, and out of this data we have to choose particular sets, or we have to do a lot of manipulation of this data to derive the specific results or specific task. So, dimensional analysis is one of the most important aspect in fluid mechanics. So, as you can see here, some of the important objectives of the dimensional analysis here I have noted. First one is choosing relevant data and presentations. So, as I mentioned, say, while conducting experiments in fluid mechanics, say, we making models for a particular prototype or particular field problem, and then that particular model should be made to certain scales, and then while deciding the scales, and then while doing the analysis, we have to see which of the important parameters to be considered in this process, and then which of the parameters should be given as input, and then which of the parameters should be measured. And so, in this aspect, one of the main objective of the dimensional analysis is to choose the relevant data, and then how to do the modeling, and then how to present it in appropriate format. So, this is possible through dimensional analysis. And then next objectives, few of the other objectives are, say, second one is data relationship and analysis. So, as I mentioned, once we get the data, we have to see that which way we can relate between the data, and then we can analyze say with respect to this data to derive meaningful relationship. And then the third objective for this particular with respect to dimensional analysis is model scales. So, as I mentioned, say, while conducting experiments in the laboratory or while representing the field problem with respect to the model, so we have to choose appropriate scales. So, the model may be very, say, very small or very medium or slightly large, depending upon the real field problem. So, the real field problem is generally we can represent very large real field problem with respect to scale down, or with respect to small scales to with respect to in the laboratory experiments. So, model scaling generally we will be getting through this dimensional analysis process. And then the another objective is here is model similitude. So, say there will be, say, with respect to the field problem and with respect to model which we develop in the laboratory, we have to see what are the similarities of which we are keeping with respect to the field problem and the model which we develop. And then finally, the theory and applications with respect to this dimensional analysis. So, that these are the objectives for this particular topic on dimensional analysis. So, as you can see here, so this is a typical model which we have developed in the hydraulics. Here you can see the model here. This is one of the model which we developed in the hydraulics lab to see the flow variations with respect to some pumps. So, here you can see a channel, a flow is coming in an open channel, and then here number of pumps are put, and then we want to study. So, this study we have done for a, say, particular power project where large quantity of water is taken, and then we have to, the purpose of this kinds of model is to see that what should be the scaling, and then what are the important parameters we have to consider, and then we have to conduct the experiments, and then we have to derive, we have to obtain the results, and then we have to get certain meaningful relationship so that we can represent the problem. So, for this particular sum model, which is some of the photographs shown here, so we first did a dimensional analysis, and then we derived a particular model scales. Say for this particular problem 1:8 scale is used with respect to the field problem, and then we will be approximating, we will be checking, we will be putting various input parameters, and then we will be conducting the experiments to derive various relationships and various to obtain various results. So, these are the important objectives with respect to this topic on dimensional analysis. So, now what is dimensional analysis? So, as I mentioned, generally in fluid mechanics we conduct large number of experiments with respect to see that how the real phenomena world real actual field problem is behaving. So, you can see that here with respect to this slide we have got a prototype of larger size, and then we will be making a small model with respect to a scale of this prototype. So, this is the prototype and a model, and so for any kind of experiments in fluid mechanics this kinds of model we will be developing, and then as I mentioned this dimension analysis one of the most important aspects which you will be using for fluid mechanics experiments and modeling. So, now just first let us see what is dimension analysis, and then let us see which are the different methods available for dimension analysis and various important relationships available with respect to the dimension analysis. So, as I mentioned here dimension analysis mainly application of fluid mechanics in engineering design to get empirical results from experiments. So, the dimension analysis is a strategy for choosing relevant data and presentation. So, say we have to choose what particular, say there will be number of variables, number of parameters will be there for which a particular problem we will be solving for or we will be looking for. So, we have to choose this relevant data for relevant parameters, and then with respect to this parameters we have to either build a model or we have to investigate the problem and then get appropriate results. So, dimension analysis is a strategy for choosing relevant data and presentation, and if factors involved in physical situations are identified, then we can see that dimension analysis form relation between them. So, if we identify, if we can find out the real factors, what are the factors which are dealing with the physical situation, then we can get various relationship using the dimensional analysis between these variables. So, thus we can see that the dimension analysis helps to develop a meaningful and systematic way to perform an experiment. So, finally, with respect to this discussion here we can see the aim of the dimension analysis is to develop a meaningful and systematic way to perform an experiment, and so that means say to perform an experiment with respect to an actual field problem we have to make a model. So, we have to scale down or we have to choose particular scale, and then we have to see that which are the important parameters or which are the factors affecting the particular problem, and then with respect to that factors we have to see that the model is made, and then we have to say conduct the experiments so that we will get a meaningful and systematic say in a systematic way we can get the results from the model. So, these are some of the say objectives or the aims of the dimensional analysis. So, now say as I mentioned the dimension analysis, so you can see that most of the physical variables or physical say parameters have dimension. So, in the dimension analysis we deal with the units and analysis of the same for a variable. So, number of variables like length, temperature, time, then say velocity or different kinds of parameters will be there for each problem. So, for each problem we have to analyze what is the typical, what is the kind of parameter, the variable and what are the dimensions for each variable. So, in fluid mechanics generally we can see that there are 5 fundamental dimensions generally we use. First one is the mass m, second one is the length represented as L, and third one is the time represented as T, and then say instead of mass sometimes we will be using in terms of force. So, force is represented as F, and then temperature theta. So, out of these 5 basic dimensions are this mass, length, time, force and temperature, and out of this, say fluid mechanics, most of the fluid mechanics problem will be generally dealing with mass, length and time, or force, length and time. So, that temperature, depending upon the problem, especially for thermodynamics problem, we will be dealing with the temperature. So, this mass, length, time and force are the 4 basic units which we will be generally dealing in fluid mechanics problem. So, and between mass and force, so depending upon the problem, sometimes we may be using mass, sometimes we may be using the force. So, generally again we can put into a system of 3 basic dimension, either mass, length and time, or it can be force, length and time, depending upon the problem. So, these are the fundamental dimensions, and then based upon these fundamental dimensions only we will be generally doing the dimensional analysis. So, now in this slide you can see some of the important units and some of the dimensions of some of the important quantities generally which we use in fluid mechanics. So, here in this tabular form it is given. So, first column shows the quantity, second column shows the SI unit and then its dimension. So, some of the important parameters which we use in fluid mechanics include the velocity, the unit is generally meter per second, and dimensions L t to the power minus 1, L is length, t is the time, and second one is acceleration, unit is meter per second square and dimension is L t to the power minus 2, and the third one is force, the unit is Newton or kilogram meter per second square. So, this is represent kilogram meters s to the power minus 2. So, the unit dimension is ml t to the power minus 2, and the third one is energy or work. The generally used unit is joule or Newton meter or kilogram meter square per second square. So, it is represented as kilogram meter m square s to the power minus 2. So, the dimension is m L square t to the power minus 2. Next one is power, represented as watt or Newton meter per second or kilogram meter square per second cube. So, it is the or it is n m s to the power 1, and dimension is m L square t to the power minus 3, and then pressure or stress, the unit is Pascal or Newton per meter square, and then its corresponding dimension is meter L to the power m L to the power minus 1 t to the power minus 2. Next one is density, it is unit is kilogram per meter cube, and dimension is m L to the power minus 3. M stands for the mass, L stands for the length, and T stands for the time. And now for specific weight, unit is Newton per meter cube or kilogram per meter square per second square. So, the dimension is m L to the power minus 2 t to the power minus 2. And then next one is relative density. So, relative density you can see it is a ratio. So, there is no dimension. And then viscosity. So, it is generally the dynamic coefficient of viscosity, Newton second per meter square or kilogram per meter second. So, kg m to the power minus 1 s to the power minus 1. So, dimension is m L to the power minus 1 t to the power minus 1. Surface tension Newton per meter or kilogram per second square. So, it is m t to the power minus 2. So, these are some of the generally used quantities in fluid mechanics and corresponding units and the dimensions. So, now before going to analyze or before we discuss the different methodologies of dimensional analysis. So, one of the important aspects which we use here in dimensional analysis called dimensional homogeneity. So, dimensional homogeneity means, so generally we will be representing say in many of the say either through experimental theoretical investigations, finally the outcome will be an equation in terms of mathematical form. And so, you can see that say with respect to this equation only we will be further investigating the problem. So, the dimensional homogeneity means, so as written in this slide here, both sides of an equation having same dimension, then that kind of equation is called the equation is said to be dimensionally homogeneous, or dimensional homogeneity is there for the problem. So, when we write the equation, both sides of the equation having same dimension. Say for example, if we consider this equation for discharge through a weir, so you can see here q is equal to 2 by 3 b into root 2 g into h to the power 3 by 2. So, here q is the discharge, b is the width of the weir, and g is the acceleration due to gravity, and h is the depth of water over the rectangular weir which we consider here. So, here you can see that this equation we can say that it is dimensionally homogeneous. So, if you analyze this equation, on the left hand side it is discharge. So, discharge unit is, say it is the unit is meter cube per second, or we can see that it is the dimension is L cube into T to the power minus 1. It is the unit is meter cube per second, so L cube into T to the power minus 1. And here 2 by 3 all these constants are there, and then B the unit is length or L, and then H the unit is L. So, L into L to the power 3 by 2, and G we have already seen is acceleration due to gravity, so meter per second square. So, if we use that, then we can see that finally the both sides the dimension will be same. So, you can see that the L cube per, so both sides of the equation we can see that having the same dimension as L cube into T to the power minus 1. So, this important aspect is used generally in the dimensional analysis for various problems. So, this dimensional homogeneity helps in checking of whether the equation which we derive is right or not. So, with respect to various experimental measurements or with respect to theoretical analysis in fluid mechanics, we will be deriving the equation. So, to see that whether one method of checking whether this equation derived is right or not is through this, to see that whether dimensional homogeneity is there. So, you can see that left hand side of the equation, the dimension should be same as the right hand side of the equation. So, this is one way of checking, and then also sometimes we may have to convert the units. So, the units may be given in FPS system or SI system. So, to convert from one unit to another, we can use this dimensional homogeneity, principle of dimensional homogeneity aspects, and then it also defines the dimensionless relationship. So, you can see that with respect to the equation which we derive. So, if the dimensional homogeneity is there, then we can say that relationships are properly defined. So, the dimensional homogeneity gives an option for checking whether the equation derived is right, or for conversion of the units from a FPS system to SI system or SI system to FPS system, like that, and also it defines the dimensional relationship between various variables. So, dimensional homogeneity is one of the important aspect in dimensional analysis, and this dimensional homogeneity is we are using, or dimensional analysis based upon the dimensional homogeneity. So, now let us see what are the importance of dimensional analysis. So, we have seen what is dimensional analysis and then the principle of dimensional homogeneity. So, now with respect to what we have discussed, so let us see what are the importance of dimensional analysis. So, first you can see in this slide here. So, some of the importance of this dimensional analysis are listed here. First one is, it is a useful method for determining the units of variable in an equation. So, if there is an equation and if we want to determine the units of a variable, we can use the dimensional analysis. So, say for example, if we consider this equation, force is equal to mass into acceleration. So, where F is force, m is mass, a is acceleration. So, the dimensions of mass is m as we have seen, and then acceleration is L into T to the power minus 2. So, hence we get the dimension of force as m L T to the power minus 2. So, like this force is equal to mass into acceleration. So, from like what we have done here, we can determine the units of a variable by using the dimensional analysis. So, this is say one of the important aspect of the dimensional analysis. And second one is, it is useful, the dimensional analysis is useful in checking the correctness of an equation derived after some algebraic manipulation. So, as we have already seen, say in fluid mechanics, we will be deriving the equations, fundamental equation, either through theoretical investigations or experimental investigations. So, in any of this case, so through dimensional analysis we can check the correctness of the equation. So, for example, we know the expression for Reynolds number as, say for in pipes, rho V d by mu, Reynolds number is equal to rho V d by mu, where rho is the mass density of the fluid, V is the average velocity, d is the diameter of the pipe, mu is the coefficient of dynamic viscosity. So, here rho is density. So, density, the dimension is m L to the power minus 3, and V is the velocity, the dimension is L T to the power minus 1, d is the length parameter diameter. So, the dimension is L, and mu is the dynamic viscosity, the dimension is m L to the power minus 1, T to the power minus 1. So, as we know the Reynolds number is dimensionless. So, we can check whether the equation is right or not. So, if we use this, you can see that this both the numerator as well as denominator have the same unit. So, we can say that the correctness or the Reynolds, the equation which we have written for Reynolds number is correct or not by doing the dimensional analysis. And then say another important aspect of dimensional analysis, it provides a meaningful way in a systematic way representation of an experiment. So, as I mentioned, we will be doing experiments to analyze various problems or to represent a field problem in the laboratory to do various testing. So, while doing these kinds of experiments, this dimensional analysis gives a meaningful way to systematically represent the problem. So, say for example, if we are interested in finding the pressure in a pipe system, we know that say if you want to find out the pressure drop in pipe system, pressure drop per unit length delta P L for particular pipe, we can see that important parameters here are diameter, density of fluid, coefficient of viscosity mu, and the average velocity V. So, here this delta P L is the pressure drop per unit length. So, from this we can see it gives an idea about the variation of parameters, and then by representing like this it gives a meaningful way of experimentation, and then through which we can get a relationship between the parameters. So, this particular problem, say pressure drop per unit length, you can say we can see that through investigations we can show that this pressure drop depends upon the various parameter like d, diameter, rho, density, and viscosity mu, and the average velocity. So, we can get a meaningful relationship. So, through this, say once we have listed the various variables or parameters, then the dimensional analysis gives a way for useful, say our dimensional analysis is useful in interpretation and representation of the results of an experiment. Say for example, in the previous problem, through dimensional analysis we can show that the relationship is d delta P L divided by rho V square is equal as a function of rho V d by mu, where rho V d by mu is the Reynolds number. So, this pressure drop is depending upon this rho V d by mu, these parameters. So, here both sides are dimensionless, and then we can further represent or we can interpret the results which we are getting with respect to the particular experiment. So, if you go for analytically to show this, it will be cumbersome, but this dimensional analysis gives a number of options to interpret the results and represent the results from an experiment in an appropriate way. So, these are some of the importance of the dimensional analysis. So, now before further going to see the different methodologies of dimensional analysis. So, what the dimensional analysis gives or the results of dimensional analysis. So, here the results of performing the dimensional analysis on a physical problem, as we have seen, maybe we may be getting a single equation, or sometimes depending upon the problem more equations depending upon the particular case. Say for example, to find the force F on a propeller blade. So, in the case of say if you want to find out the force on a propeller blade for a typical problem. So, you can see that this force depends upon the diameter, and then the forward velocity of propeller u, fluid density rho, revolutions per second n, fluid viscosity mu. So, we represent this the force on the propeller as F as a function of d u rho n and mu as described here, or this we can write now with respect to this we can write as another function phi 1 as a this dependent variable also is a parameter. So, here phi 1 as a function of f d u rho n mu, and then we can equate to 0. So, you can see that this phi and phi 1 are the unknown functions here. So, through the dimensional analysis we will be trying to find out this unknown functions for the particular case. So, you can see that for this particular problem, for the particular case of force on a propeller blade. So, if you write say F is equal to k, a constant k multiplied by d to the power m, u to the power p, rho to the power q, n to the power r, mu to the power s. So, here as I mentioned, F is the force and d is the diameter, u is the velocity, rho is the density, n is the revolutions per second as we have seen, and then mu is the viscosity. So, here k is an unknown constant, and here this small m, p, q, r, s are the unknown constant powers. So, through the dimensional analysis what we are finally finding out this constant values, whatever the constant values, and then finally we will be able to get a relationship. So, through the dimensional analysis what we are doing is number 1 to obtain this m, this constant k or m, p, q and r, s, and second aim is or second objective is to form variables into several dimensionless groups. So, say for example, here we have now put this phi 1 as in terms of phi. So, we can form different dimensionless groups. So, here we may get k or phi 1 we may get through experiments, and then dimensionless groups helps in deciding what measurements be taken. So, these are the outcome from the dimensional analysis for a typical problem. So, for a typical problem which may be doing experiments or which may be even doing theoretical analysis. So, in both cases the aim is say we are representing terms of an equation, and then we will be trying to obtain the unknown constants and then finally form a relationship with respect to the dimensionless groups. So, these are the important objectives and the results or the outcome from the dimensional analysis. So, now we have seen the objectives of dimensional analysis, say what are the outcomes and then what are the importance of the dimensional analysis. Now, next is we will discuss the important methodologies of dimensional analysis. So, generally in literature, in various standard textbooks, you can see two methods for dimensional analysis. First one is called a Rayleigh's method, and second one is called a Buckingham's pi theorems. So, here we will be discussing both of these methodologies with respect to examples. So, first one Rayleigh's method. So, this is a simpler method of dimensional analysis for small number of parameters. So, this some of the advanced books you can see only one method as Buckingham method. So, this Rayleigh's method is the difficulty is that this we cannot extend to large number for a problem where large number of parameters are there. So, but this is much more suitable, this Rayleigh's method is much more suitable for a problem where small number of parameters are there, and then dependent variable is can be expressed as the function of independent variables with their exponents and multiplied with a constant term. So, in the Rayleigh's method it is one of the simple method, and then it is applicable for a particular problem where the number of parameters are less, and then for a particular problem for the dependent variable, if we can express as the function of independent variable, this method can be easily applied. So, further say as we have seen, say generally the particular problem we will be trying to express in terms of the fundamental dimensions, either mass, length or time, or force, length or time. So, with respect to this we will be having some of the exponents, unknown exponents as we have seen in the previous slides. So, exponents of the fundamental dimensions of the parameters are, so in this Rayleigh's method, So, what we do, the exponents of the fundamental dimensions of the parameters are equated from both sides of the equations. So, we will be discussing further with respect to an example. So, the method, the say for the typical equation, we will be finding out these exponents, the unknown exponents, by equating both sides of the, say equating the with respect to dimension, both sides of the equations are equated to get the unknown parameters. So, the exponents are found out from the equations, and here you can see the method is much more simple, and wherever for small number of parameters involved. If large number of parameters are involved for a particular problem, the method is much more cumbersome, since this method cannot deal a large number of parameters. So, to further illustrate this Rayleigh's method, we will discuss a typical problem. The problem is the drag force. To find out the drag force Fd on a spherical body, we can see it is dependent upon the density of fluid, diameter of the sphere, the velocity of flow, and coefficient of dynamic viscosity mu. So, we have to obtain an expression for the drag force using Rayleigh's method. So, here you can see that here there is this is this sphere which we consider. So, the flow is coming and it is flowing over the sphere. So, we want to find out what is the drag force. We want to get an expression for the drag force with respect to various parameters involved. So, this is the problem. So, now the different steps. So, step by step we will proceed. So, as I mentioned earlier, so first step is we have to identify for the given problem what are the important parameters which will be. So, here we have to find out the drag force for the flow over a sphere. So, the important parameters, you can see that here the important parameters, the viscosity of the fluid mu, and then of course, the diameter of the sphere is very important, and then the approach velocity of the flow, or the average velocity of flow v is important, and then of course, the density of the fluid. So, the first step in this Rayleigh's method is to express this Fd, the drag force, as a function of these important parameters mu, d, v and rho. So, we write the drag force Fd is equal to as a function of mu, d, v and rho as in this first step, and then now you can see that now we wrote a function. So, generally we can represent in this Rayleigh's method, we represent this Fd is equal to multiplied by a constant k into d to the power a, v to the power b, rho to the power c, mu to the power d, where k is a constant, a, b, c, d are the unknown exponents. So, the Fd is represented as k into d to the power a, v to the power b, rho to the power c, mu to the power d, where mu, d, v, rho are the parameters for this particular problem. So, now here as I mentioned, we will be using either mass length time units or force length time units for the dimensional analysis. So, either one of this can be used. So, here we are dealing with the drag force. So, let us try to solve this problem by using the FLT system or force length time system. So, here now this drag force, we can see that drag force, if you write in terms of the unit, you can see the unit is force. So, we can just represent as F. So, F is equal to, then k is a constant. So, k has no unit. So, d is the length represented in terms of L. So, L to the power a, and then velocity, the dimension is L into t to the power minus 1. So, here we write L into t to the power minus 1 to the power b, and then density, as we have already seen earlier, can be represented as F into L to the power minus 4 t to the power 2. So, rho to the power c is represented as F L to the power minus 4 t to the power 2 all to the power c, and then mu is the viscosity. So, that is represented as F into L to the power minus 2 into t. So, mu is represented as this, and then to the power d, that is. So, finally, we write in third step, we write in FLT system like this. So, now both sides we have units, and then say here the unknowns are a, b, c, d. So, here now to find out what will be the value of this ABCD, what we can do is we can equate the exponents of the fundamental dimensions with respect to the right hand side and the left hand side. So, you can see that left hand side is the unit is force. So, it has got a say f as the dimensions. So, f to the power 1. So, we have the left hand side is known. So, but right hand side the unknowns are A, B, C, D. So, now with respect to this we can write here 3 equations. So, since we have got 3 fundamental dimensions. So, here if you get, you can see that force is concerned here two places. So, with respect to left and right of this equation we can write C plus D is equal to 1, and then if you equate with respect to length L, we can write A plus B minus 4C minus 2D. Here left hand side it is 0. So, that is equal to 0, and then with respect to T we can write here T to the power minus 1. So, minus B, then plus here T to the power 2 or to the power C. So, plus 2C, then here T to the power D. So, plus D. So, minus B plus 2C plus D is equal to 0. So, here we get 3 equations, and unknowns are 4 unknowns A, B, C, D. So, number of unknowns is greater than the number of equations. So, we have to remodel this system of equations. We can write out of this 4 in terms of say out of the 4 equations we can write with respect to other parameters A, B, C, D. So, this can be done here. So, let us express A, B, C in terms of D. So, that is we have C is equal to 1 minus D, B is equal to C plus D, that is equal to 2 minus D. So, that we get A is equal to minus B plus 4C plus 2D, that is equal to 2 minus D. So, finally, with respect to this equation we can write F is equal to K into D to the power 2 minus D. So, now C is represented as 1 minus D, B is represented as 2 minus D, and A is also represented as 2 minus D. So, we write F in the 7th step we write F is equal to K into D to the power 2 minus D, V to the power 2 minus D, rho to the power 1 minus D, mu to the power D. So, now we can see that here if you get with respect to this the equation for the f and then other terms we can see we can get the value of D. So, finally, here if you solve this system we can write the system as f is equal to. So, here you can see that this the left hand side there is no f term. So, obviously, for this typical case it should be say coming this way. So, we write f is equal to k d square v square rho into mu by rho v d to the power d. So, this equation is represented this form. To finally get the drag force F d is equal to rho d square v square and as a function of mu divided by rho v d. So, this is the final expression. So, this is the way which we do the dimension analysis using the Rayleigh's method. So, we start with so first in the first step we see that what are the important parameters, and then we represent the dependent variable with respect to these parameters as a function, and then we put the fundamental dimensions for each either in terms of mass length time or force length time, and then we equate with respect to the exponents, and then the unknown exponents are found, and finally we derive the system of equation as for the drag force. So, for drag force here we obtain rho d square v square and as a function mu d by rho b d or d v rho as shown. This is the final expression. So, here you can see that this now while doing experiments for drag force, this equation helps to obtain particular relationship and then to solve the problem in a meaningful way. So, this here now through this example we have demonstrated the Rayleigh's method. So, now Rayleigh's method, as I mentioned, it has got some disadvantage. The number of variables are very large or number of parameters are very large. It is very difficult to deal with. It is the system become quite complex. So, to deal these kinds of problems, the further the method used is called Buckingham pi theorem. So, this is the most Buckingham pi theorem is the most commonly used method. So, here in Buckingham's pi theorem, so Buckingham pi theorem most commonly used, and it is also known as method of repeating variables. So, here you can see that when we discuss many of the problems say in fluid mechanics, there can be variables will be repeating. So, this aspect of repeating variables are taken care by in this method Buckingham pi theorem's method. So, that is why sometimes this method is also called as method of repeating variables. So, here in this Buckingham's pi theorems, we do the dimensional analysis by a series of steps. So, here this pi, the word pi refers to dimensionless group or the product of variables. So, the word pi which here we refer is refers to dimensionless groups or products of variables. So, now we will discuss the details of Buckingham's method. So, Buckingham's pi theorem is mainly, or this method is mainly based on two theorems. So, first one is, so here both the theorems are written. So, first theorem is a relationship between m variables can be expressed as a relationship between m minus n non-dimensional groups or pi groups of variables, where n is the number of fundamental dimensions like a m l t, as we have seen, required to express the variables. So, the first theorem of Buckingham is a relationship between, if m variables are there, then a relationship between m variables can be expressed as a relationship between m minus n non-dimensional groups of variables, where n is the number of fundamental dimensions. So, for a given problem, if there are m variables and we identify n fundamental dimensions, so now we can have m minus n relationship, or this called non-dimensional group or pi groups required to express the variables. So, this is the first pi theorem, and the second pi theorem is each pi group is a function of the n governing or repeating variables plus one of the remaining variables. So, the second theorem by Buckingham is each pi group is a function of the n governing or repeating variables plus one of the remaining variables. So, the Buckingham pi theorem or Buckingham method is of dimensional analysis based upon these two theorems. So, we have to identify what are the m variables, and then we have to identify the fundamental dimension, n fundamental dimension, then we try to represent this with respect to m minus n non-dimensional groups or pi groups, and then each pi group is we have to form as a function of governing or repeating variables plus one remaining variable. So, this method is based upon these two fundamental theorems. So, now in the Buckingham pi theorems we use the step by step method. So, we will be starting with the various steps and then further proceeding. So, here the Buckingham pi theorem method, the various steps are mentioned here one by one. So, first step in the method is list the variables involved in a given problem. So, as we have seen, if there are m variables, so we have to list the variables like velocity, diameter, coefficient of viscosity, density, or what kind of the variables. So, we have to list the variables. So, that is the first step. So, let the number of variables be m. So, second step is express the variables with their dimensions. So, as we have seen, the velocity is L into t to the power minus 1, or the unit is meter per second. So, we have to express each variables with respect to the fundamental dimensions, either in terms of m L t or mass length time, or f L t force length time. So, now the second step is we will be expressing the variables with their dimensions, and the third step is find out the number of fundamental dimensions involved. So, whether it is MLT or F or all this, or if temperature is also involved, that is also to be identified. So, the third step is find out the number of fundamental dimensions, and then next step is determine the number of pi terms required. So, we have already seen what is pi term, it is this m minus n. So, we have to determine the number of pi terms. So, number of pi terms is equal to m minus n. So, now based upon this we select the repeating variables is equal to number of fundamental dimensions, and then further we express the pi terms as product of the repeating variables having exponents with a non-repeating variables, so as to make the equation dimensionless. So, in the next step here we express the pi terms as a product of repeating variables. So, for example, pi 1 is equal to u to the power a, v to the power b, w to the power c into z. So, where u, v, w are the velocities which are the repeating variables and z is a non-repeating. So, we express pi 1 is equal to u to the power a, v to the power b, w to the power c into z. And next step is, after this above step is repeated for all non-repeating variables. So, like this we repeat for all non-repeating variables, and finally, we express the final relationship among the pi terms as pi 1 is as a function of pi 2, pi 3, pi 4, etc. If r repeating variables are there, pi r. So, finally, we express the final relationship between among the pi terms as pi 1 is equal to a function of pi 2, pi 3, etc. So, now we have seen the different steps. So, in the Buckingham pi method, we have a series of steps. We will be identifying the variables, and then we will be forming the pi groups, and then we will be writing with respect to the repeating variables as step by step. So, to illustrate this Buckingham pi method, here a small problem we will discuss. So, the problem is to find the pressure drop per unit length for the steady flow of an incompressible Newtonian fluid through a long smooth walled horizontal circular pipe. So, here you can see pipe, a smooth walled pipe, horizontally position in horizontally. So, let the diameter of the pipe is d, and then the velocity, average velocity is v, the viscosity of the fluid passing through the pipe is mu, and rho be the density. So, we want to find out the pressure drop per unit length. So, by using the Buckingham's pi method. So, here the important parameters are, so here including this we have to find out the pressure drop. So, that is let us represent delta p subscript L, delta p L. So, the variables are delta p L, the diameter d, and the velocity v, the viscosity mu, and the density rho. There are 5 variables included for this particular problem. So, we can represent, since our aim is to get an expression for delta p L. So, we will write delta p L is as a function of d, rho, mu, and v. So, the parameters can be expressed as, so for each variable we will represent in terms of the fundamental dimensions. So, v is represented as L into t to the power minus 1, mu is represented as f into L to the power minus 2 t to the power 1, and rho is represented as f to the power 1 L to the power minus 4 t to the power 2, and d is the diameter represented as L, and the delta p L, which is the delta p subscript L, which is the pressure drop. So, that is represented as f into L to the power minus 3. So, here the fundamental dimensions are f, L, and t, force, length, and time. So, you can see that we have got 5 variables including the pressure drop, and then we have got 3 fundamental dimensions. So, n is equal to 3, m is equal to 5. So, we can form 2 pi terms. So, 5 minus 3 is equal to 2. So, let us choose v, d, and rho as the repeating variable initially for this typical particular problem. So, that we can write that pi 1 is equal to delta p L d to the power a, v to the power b, rho to the power c. So, if we choose v, d, rho as the repeating variable, so a, b, c are constants which you have to find. So, that we can write now with respect to this pi term. If you write all the units with respect to what is given here. So, f into L to the power minus 3, L to the power a, L into t to the power minus 1, all to the power b, f to the power 1, L to the power minus 4, t to the power 2, all to the power c. So, right hand side is pi 1, which is a dimensional. So, f to the power 0, L to the power 0, t to the power 0. So, now here we can solve for this with respect to the a, b, c, and the given on the right hand side we can solve for the unknown constants exponents a, b, and c. So, if you solve this, we will get a is equal to 1, b is equal to minus 2, and c is equal to minus 1. So, now, so that we can write pi 1 as, so once we get a is equal to 1, b is equal to minus 2, c is equal to minus 1, we can write pi 1 is equal to d into delta PL by rho v square. So, this is the first pi term pi 1, and similarly now let us represent pi 2 as pi 2 is equal to mu into d to the power a, v to the power b, rho to the power c. So, as we have done earlier, we can find out here a, b, c. So, we can see that a is equal to minus 1, b is equal to minus 1, c is equal to minus 1. So, finally, we get pi 2 is equal to mu divided by rho v d, or this mu by rho v d can be also expressed as reciprocal of this as rho v d by mu also. So, we get both the pi 1 and pi 2 which are dimensionless group here. So, the resulting expression we can write as d into delta PL by rho v square as a function of phi of mu by rho v d, or d into delta PL by rho v square as function of rho v d by mu. So, this is the resultant expression with respect to the dimensional analysis which we did here by using the Buckingham pi theorem. So, further we will be discussing the various applications of this Buckingham pi theorem and its importance further. So, this is one of the simple application how we solve a typical problem using the Buckingham pi theorem.